Swayam Prabha. Digital India. Educated India.
Welcome everyone. So this is the 6th tutorial session on geology and soil mechanics. Now today we are going to discuss the last chapter regarding the tutorial session, the shear strength of soils. So we are going to start with a problem that was given for assignment, and then we are going to proceed to the next problems in the chapter. So the problem that was given in the assignment was consolidated undrained triaxial test is performed on a clay sample of low plasticity whose gamma d, or the dry unit weight, is given as 1.7 into 10 to the power 4 Newton per meter cube. Now the sample was recovered from a depth of 8.15 meter. The porosity of the clay sample is given as 0.35, and the consolidated undrained triaxial test gave the value of phi Cu as 14 degree and CCu as 4 into 10 to the power 4 Pascal. So it is asked, determine the UCS, or also known as the unconfined compressive strength of a saturated sample of this clay from the same depth, assuming SR, or the degree of saturation, equal to 1, and that no moisture was lost during the process of handling. Now we all know that the unconfined compressive strength, or UCS, is generally given by 2 into Cu, where Cu is generally given as the undrained cohesion. Now you have to find out this parameter Cu from the given phi Cu and Ccu. So first let us draw the Moore circle condition for the consolidated undrained test. So this is how the Moore circle looks like. This obviously is CCu, this is phi Cu, this point is touching, and we all know that this value is Cu, or the value of undrained cohesion, because as you all know that during a UU test, irrespective of whatever the pressure is, let us say that the pressure here is sigma 1, here the pressure is sigma 1a, this is sigma 1b, and this is sigma 1c. So irrespective of whatever the pressure is, your mode circle here, the failure line is always a horizontal line, and it has a phi equivalent to 0, and this value is equivalent to Cu. So that is what I have also drawn here, that this value is actually equivalent to Cu. Now you have to derive the expression from Cu from the given Ccu and phi Cu. Now you have to know at first that what happens during a consolidated undrained test. So during a consolidated undrained test, the first process that occurs is consolidation. Now during the process when consolidation occurs, the consolidation pressure is same throughout the test. So let us consider that the consolidation pressure is sigma naught. Now this is same during the entire process of consolidation. This is also termed as the confining pressure, or given by the term as sigma 3 in case of a, specifically in case of a triaxial test. Now at the end of the consolidation, U is equivalent to 0, or the excess pore water pressure has been dissipated, since drainage occurs. Now at the beginning of the shearing stage, or at the beginning of the undrained phase, what will happen is that this confining pressure sigma 3 will remain as the same, while depending on whether it is a stress control or a strain control test, you are going to change the principal stress, that is sigma 1, which is also known as sigma 3 plus del sigma, where del sigma is the deviatoric stress. Now these are all covered in the lecture, so I am not going to discuss them in very details. So this sigma 3 is same as the consolidation pressure sigma naught, while depending on the stress control or the strain control test, you are going to increase the del sigma, and you are going to achieve sigma 1, where basically different values of failure will occur. Now let us say that, so at the beginning of the shearing stage, so sigma 1, so at the beginning of the shearing stage, the confining pressure is sigma 3. Now at the end of the test, no more drainage is allowed, because during the entire undrained phase no more drainage is allowed. So some amount of pore water pressure is developed. So U is not equal to 0 at the end of the shearing stage. And at this point what has happened is that this sigma 3, which was initially confining pressure at the beginning of the consolidation, at the end of the consolidation phase, as well as since U was equal to 0 or drainage has occurred, this was equivalent to an effective stress as well. So this was all, this can be also termed as effective confining pressure, has now moved to total confining pressure. After shearing, because U is no longer equivalent to 0. So the effective confining pressure at the end of the consolidation stage has now become equivalent to total confining pressure at the end of the shearing stage, because the pore water pressure is not 0 because of the undrained sample. Now let us figure out that how do you find out this value of C. So this is the failure line, this is the failure line, and obviously this is the Cu, this one is Cu, this one is phi Cu. Now it will intersect, the Cu will intersect at this point, because this is the shear strength, You can see that this is the Mohr Coulomb failure line. For consolidated undrained, and obviously this Cu line, which basically has a phi equal to 0, will intersect the circle at this point. So from here we can find out if R is the radius of Mohr's circle, then Cu is equivalent to sigma 1 minus sigma 3 by 2, which is equivalent to R. This is known to everybody because this comes from the basic relation of performing a UU test, where basically UU test is the peak point of the Mohr circle. So obviously this is equivalent to sigma 1 minus sigma 3 by 2 equal to R. Now for our condition, since you considered that sigma 3 is equivalent to sigma naught, so we will take sigma 1 minus sigma naught by 2 equivalent to R. Another important point is that this R, let's consider this point as A, this point as B, and this point C, this is D. So we can write AB by AD is equivalent to sine of phi CU, because obviously this is the sine of phi CU because this is perpendicular always. So this point is also perpendicular. So obviously perpendicular by hypotenuse is equivalent to sine phi. So that is what we have written. Now what is AB? AB is nothing but actually the radius of Mohr's circle. So we can write this as R. What is AD? AD, as you can see, this point is sigma naught because this is at the end of the shearing stage. So this point is sigma naught, this point is sigma 1. If this is true, then AD is equivalent to sigma naught plus R plus C of Cu into cot of phi Cu. Now this can be also derived from the basic relation. So I am not going into the details, but if you can see from the geometry, you can easily derive this relation, because sigma naught is the point from C to A, CA. R is basically A sigma naught, and CCU cot phi is nothing but this length CD. So obviously if you add all together, you will get sigma naught plus R plus CCU cot phi. Now we put back in the original relation. So R by sigma naught plus R plus CCU cot phi Cu is equivalent to sine phi Cu. So Cu from here is sigma naught plus Cu into sine phi Cu plus Ccu into cos phi Cu. Now this is what is the relation of the UU test with the CU test, or basically this is the relation of the undrained cohesion with the consolidated undrained cohesion and consolidated undrained friction angle. Remember that it should not cross. You should always remember that when basically you are drawing the Mohr circle for a CU test, it should never cross the CU line, or the failure line should never cross the peak, because the same Mohr circle may not apply for an unconsolidated undrained test. It is obvious that all these lines will intersect at the common point of failure, but it is always advised that the Mohr circle may not be same in each one of the tests. For a consolidated drain test it may be different, for a consolidated undrained test it may be different, for an unconsolidated undrained test it may be different, for a UCS test it may be different, but they will always have the same common failure point. So that is what I have drawn here. I have just let it pass to the common failure point, and I have derived this relation between Cu and phi Cu. So once this relation is derived, now you have to find out what is the value of sigma naught dash. Now obviously sigma naught dash corresponds to the overburden effective pressure sigma V dash at depth h. So sigma naught dash is then equivalent to sigma V dash, which is equivalent to gamma dash into h. Now gamma dash obviously is known as gamma sat minus gamma w. So gamma sat you can easily find out from the relation of gamma dry, because gamma sat is GSC plus E by 1 plus E into gamma w, while gamma dry is equivalent to GS by 1 plus E into gamma w. So from these two relations you can easily find out, because E is given in terms of porosity, and you know that E n is equal to E by 1 plus E. So E is obviously given to you. So from these relations it turns out that gamma set is equivalent to 2.05 into 10 to the power 4 Newton per meter cube. So sigma V dash or sigma naught dash is actually equivalent to 2.05 into 10 to the power 4 Newton per meter cube minus gamma W equivalent to 8.56 into 10 to the power 4 Pascal. So this is basically the sigma V dash or the stress at that point into H, sorry, the height. So this is basically equivalent to the stress at that point. So the sigma naught dash now you have found out as 8.56 into 10 to the power 4 Pascal. The depth is already given as 8.15 meter. So H is equivalent to 8.15 meter. So if you put all these values in this, Cu is equal to sigma naught plus Cu sin phi Cu, Cu cos phi Cu, then we will get Cu as 8.56 into 10 to the power 4 sin 14 degree and by 1 minus sin 14 degree, that is 5 sigma naught plus Cu sin phi Cu plus Ccu cos phi Cu. So plus 4 into 10 to the power 4 cos 14 degree by 1 minus sin 14 degree. Obviously this number is the Ccu, 4 into 10 to the power 4 pascals. So from here you get that Cu is equivalent to 7.85 into 10 to the power 4 pascals. So obviously the UCS or the unconfined compressive strength is 2 times of Cu, which is 1.57 into 10 to the power 5 pascals, given that Cu is equivalent to 7.85 into 10 to the power 4 pascal. So this is a simple derivation that how basically you can connect one triaxial test with another, like let us say a Cu with a UU, or you can also connect CD with a CD with a Cu, but it is very difficult to connect a consolidated drain test with a UU test, because an UU test, in case of a UU test, you see that all the mode circles are almost the same. So that is why the effective stress effective mode circle is actually absent in all those cases. Now a general relation that basically describes the unconfined compression test or a UU test and a CU test has been derived in this formula. Now let us move to the next problem, where basically we will discuss something about how the strain rate, and in a strain control test, let us say the strain rate, or basically in an overconsolidated soil, how the overconsolidated soil will affect the behavior of the mode circle. So the second problem says that several triaxial tests have been performed on identical clay samples. The variation in test procedures for samples X and Y has been varied by 1 factor. Now this is a more kind of explanatory problem rather than a solving problem, so we will discuss this problem, and it is asked that for which of the conditions below sample was subjected to higher shear stress value. Now the first question is that a consolidated drain test is performed. Now as you all know, in a consolidated drain test, it's entirely a effective stress test and it's a very slow test. So a consolidated drain test consists of a consolidation phase and a drainage phase and a drained phase. In both the cases, the total stress is always equivalent to the effective stress, because in each of these cases the pore water pressure or the excess pore water pressure is always equivalent to 0. So it is said that the consolidation pressure is sigma 3 and the strain rate is varied in this test. So this is a strain control test. Now our discussion about strain control test and stress control test has already been discussed in the lectures, in the lecture slides, so I am not going to discuss all these things. The first thing is that here the strain rate of X is 1 millimeter per minute, while that of Y is 0.005 millimeter per minute. Now in which of these cases you will see that the sample is subject to high stress value. So how do you find out this? So the first question is that, now you all know that for all triaxial tests, two Morse circles are present. So one of them is called the effective Morse circle, and the other of them is the total Morse circle. Now you also know this, that the total is actually given by effective plus or minus u, depending on whether the sample is dense or loose in case of sands, or NC or OC in case of clays. So depending on that, if the test is CD test, then just I have said previously that the total is actually equivalent to effective, because the U is always equivalent to 0 whether it is a consolidation phase or it is a drain phase. And one important thing, that what is the high stress value? Now in this case, that high stress value is basically which one has a maximum shear stress at failure is the one that basically has a high stress value, because you know this, that a soil is always subjected, or a soil sample is always subjected to only shear, and in compression or tension, in compression it will never fail, in tension it cannot take tension, so obviously it fails whenever a tension is applied. So only failure that you observe is basically in case of shear. So that is why the maximum shear stress at failure, the high stress value means the only stress that here is referred to is the maximum shear stress at failure. So in the first case, let us say a strain rate of 1 millimeter per minute is applied to sample X. Now clays have a very low coefficient of permeability. We all know this from our permeability chapter. So the sample Y is 0.005 millimeter per minute. So 1 by 0.005, the ratio R, it comes out to be about 200 times. So that first test goes 200 times faster than the second test. Now as the sample in case of clays has a very low coefficient of permeability, so obviously a higher strain rate will not encourage the drainage, rather it will prevent the drainage in this case. So clays have a very low coefficient of permeability, so basically the pore water pressure or U would generally what we do is that since the pore water pressure distribution may not be uniform, so we will consider that, let us say that this is the triaxial sample. So this is, let us say, 38 millimeter, and this is, let us say, 76 millimeter. So the pore water pressure distribution along the sample may not be uniform. It may be somewhat like this, it may be like this, depending on where the drainage is opened or where the drainage is closed. So the pore water pressure may not be uniform. So we will consider only at the mid height u. Okay. So at mid height, and we will consider that mid height pore water pressure to be representative of the entire sample. So at mid height, pore water pressure or u at failure is, let us say, uf. Now since basically you see that in case of x, basically the strain rate is much faster, so in this case drainage is not supposed to occur. So if drainage is not supposed to occur, then obviously the sigma dash will be equivalent to sigma minus u. So in this case, since it is sigma minus u, so the total stress, even though may be higher, the effective stress is reduced. Now this is considered, all things are considered considering that the sample is actually normally consolidated. NC OC is just a special case, so that is why we are considering only normally consolidated sample. So sigma dash is equal to sigma minus u. So obviously you have to plot the Mohr circle with the effective stress, because you have to get the effective parameters. The effective parameters are more important rather than the total stress parameters. We have seen that from the consolidation itself, because whenever you are supposed to find out, let us say the settlement delta S, or let us say the shear strain tau f, you are always considering the effective stress parameters rather than the total stress parameters. So for a normally consolidated clay, if basically the sample is undrained, then basically the strength is reduced. So in that case, you will see that sample Y, where basically the strain is much less, is subjected to higher shear stress than sample X. You can also think this from this point of fact, that in case of sample Y, the sigma 3 dash is also reduced, because you see that at the end of the consolidation phase, both the samples are at the same stage. So obviously at the end of the consolidation stage, even this sample has a sigma 3, even this sample has sigma 3 dash, this sample has sigma 3 dash as the effective confining pressure. While immediately when the test starts, then what will happen is that since the strain rate in the sample X is much greater than the sample Y, so what will happen is that in internal pore water pressures will develop. So this sigma 3 dash then will reduce to sigma 3, as I have said in the previous question as well, that say sigma 3 will be now equivalent to sigma 3 dash will be equal to sigma 3 minus u. So this sigma 3 dash will be equivalent to now sigma 3, and u will be the pore water pressure. Now since it is a normally consolidated clay, so obviously the sigma 3 dash at the end of the shearing will be less than the sigma 3 at the end of the consolidation stage. So obviously X is subjected to a less confining pressure than Y, and this leads to the peak stress of sigma 1 dash less for X less than sigma 1 dash for Y. So obviously sigma 1 dash X minus sigma 3 dash, so obviously the failure or sigma at failure for X will be less than sigma at failure for Y. So the shear stress for X, or shear stress basically for the sample X, will be less than the shear stress from the Y. Now let us try to draw the Mohr circle and see how this comes out to be. So this is our sigma tau envelope. So this is the sample sigma 3 at the for the sample X, let us say, at the end of consolidation. So obviously this sigma 3 is equal to sigma 3 dash for X at the end of consolidation, and similarly for Y also it will start from the same point. So obviously it will start from here, Y. Now as you can see that after, since it is a now it has become an undrained test, so obviously the effective stress now will go back. So this is the sigma 3 dash for x, and this difference is given as u, or the pore water pressure that is developed during the sample x. So, for y, obviously the diameter will be greater than x. So, obviously the shear stress in this case is greater. Now, let us move to the next part or the next question. So, we have known that basically with the increase in strain rate, in case of a consolidated drain test, you should decrease the strain rate as far as you can, but with the increase in strain rate, what will happen is that the strength is going to reduce and you are not going to get a consolidated drain test, rather you are going to go through consolidated undrained tests, where basically the shear strength may not be the desired shear strength that you actually wish to find out. Now, let us consider another consolidated drain test for the same sample x and y. In this case, the sigma 3 is 0.3 MPa. Sample x was subjected to a sigma p dash. Now, you know from your definition of consolidation, the sigma p dash is the pre-consolidation pressure. So, sigma p dash is 0.2 MPa and the strain rate is 0.005 millimeter per minute. So, if you remember the stress paths P and Q, so for the sample x, basically it started from here and it moved along this line, just because you see that during a consolidation phase there is no shear stress. So, obviously it was subjected to along this line because there was no shear stress. So, Q is equivalent to 0. So, this point is 0.2 MPa and then it was sheared, and then it was sheared. A pre-consolidation pressure of 0.2 MPa was applied and the consolidation pressure was 0.3 MPa and then it was sheared. This for the sample x. Now, for the sample y, the sigma p dash or the pre-consolidation pressure was 0.4 MPa and the strain rate is 0.005 millimeter per minute. So, in this case what happened was that, if this is QP, the sample started from this point, it moved along this line to 0.4 MPa, then it reverted back to this point 0.3 MPa and then from here it moved along. So, you see in one of the cases basically what happened, the pre-consolidation pressure that was subjected, or sigma p dash, is greater than sigma 3 or sigma c, the consolidation pressure. This is in case of sample y, while in case of sample x, the sigma p dash is less than sigma 3 or sigma c. Now, this will point out one important thing, that what you should do in case of a track shell test and what you should not, or basically whether you should subject it to a stress that is greater than the consolidation pressure or not at any condition. So, if you go back to the original definition of consolidation, then you remember that in a consolidation curve, if your sigma naught, let us say you start from here and your pre-consolidation pressure is sigma p dash, and let us say that if in case of pre-consolidation pressure you move along this line and then you come back at this point sigma naught dash, and then you can go back here, this pre-consolidation pressure, then the void ratio in this case is less compared to the case where basically you just move along this line and move at a point that is greater than the pre-consolidation pressure. E1 is less than E2. So, if you cross a pre-consolidation pressure and after that, or if you go to the pre-consolidation pressure and then you revert back to a position that is less than the pre-consolidation pressure, it is obvious that since the soil has been subjected to a stress history that is greater than the present stress history, which is an example of an over-consolidated soil, the void ratio in the first case will be much less than the void ratio in the second case. So, in this case, this sample is much more densified than this sample. So, obviously, if a sample is densified, then obviously the sample for the Mohr circle for a densified sample will have a high shear stress compared to the Mohr circle for a loose sample. That is what generally happens. So, in this case also, the sample y was subjected to greater sigma p dash. You can easily see from here, from this figure, that you are going back, means this is what this should be, the what the void ratio should be. So E is the difference in the void ratio that is created due to the between the initial and the final part, due to the reverting back to the stress of less than the pre-consolidation pressure. So obviously this is an example of OCR, or over consolidated soil, over consolidated clay, while this is an example of NC, normally consolidated clay. So since it is an OC clay, so obviously this it is will be subject to a greater sigma p, because you all know that for an OC clay the graph is somewhat like this, but for an NC clay the graph is somewhat like this. So at residual state they meet at the same point, but actually at the ultimate state it is obvious that a normally that a OC clay will have a greater strength than an NC clay. So Y was subject to a greater sigma p dash, so it behaves as an OC clay, so obviously the shear strength or shear stress is greater. So let us draw the Mohr circle in this case. This is sigma 3 dash, let us say, and this is sigma 1 dash for, let us say, y, and this sigma 1 dash for x. Now here in this case the strain rate is very less, so obviously whether you go for an x or whether you go for a y, in both the cases the effective stress is equivalent to the total stress. Now remember that all these cases are regarding only one soil sample only. If basically the two soil samples are entirely different from one another, in that case obviously the dense sand and the loose, the dense or the loose may not behave in the same way. That means they may both have the same peak, but since in this case both the soils, just only one difference is there, that one of them is over consolidated while the other of them is normally consolidated. That is why the peak in case of an over consolidated clay is greater compared to that of a normally consolidated clay. You can also think it from the point of the pre-consolidation point of view, or as I have showed from the simple consolidation graph. Moving to the third problem, it is said that the sigma 3 is same while sample y is a CD test, sample x is a CU test. Now if you can remember this correctly, then this is same as compared to the first problem, because in the first problem also we said that since the strain rate in case of sample x was higher, so actually it was a CU test rather than a CD test. So in this case also the shear stress or basically the shear strength of x will be greater than that of the y. But remember that this is not always the case. In certain cases it may so happen that the in case of a consolidated undrained test the strength is low compared to that of the consolidated drained test. So in this case you should keep in mind, you should not think this as a general recommendation that always in case of a consolidated undrained test the strength is less than that of a consolidated drained test, the effective stress is always less than that of a consolidated drained test. It may sometimes happen that it may be greater, but it depends, it all depends on how you prepare the sample, or whether the same samples are considered or not, or whether there will be what will be the packing void ratio, what conditions you are subjecting it to. So depending on all these cases these things are happening. So in this case also x is a CU test, so obviously in this case the effective stress for x will be less, because the sigma 3 or the consolidation pressure for both x and y at the end of the consolidation was same. So sigma 3 dash is equal to sigma 3 dash at the end of consolidation for x and y. But then what happened was that in one of the cases it was an undrained test, while in the other case it was a drained test. So sigma 3 dash in one of the cases reduced from the sigma 3c at the end of consolidation, while in the other case it was the same. So since at x it was subjected to a lower confining pressure, so obviously the shear stress in this case is less. And as you can remember that the graph is somewhat like this, and so this is for x while this is for y, this is sigma 3 dash, this is sigma 3, this is sigma 1, and this is sigma 1 dash for x, sigma 1 dash for y. So obviously x is subjected to a lower shear stress compared to that of y. Now for the fourth problem, it is said that both samples are over consolidated to 0.6 MPa. Now sample X is drained and consolidated to 0.2 MPa. Now drained and consolidated means it is a consolidated drain test. So 0 0, then it moved back to 0.6 MPa, this is P, this is Q, and then it reverted back to 0.2 MPa. So this is an example of an OC soil, and then it moved along this line 3:1. That is how it happened in case of X. For Y, basically it is said that it is undrained and consolidated to a pressure sigma 3 such that sigma 3 dash at failure is equal to 0.2 MPa. Now in this case Y is undrained and consolidated. So since Y is undrained and consolidated, now we have to first plot that the limit state conditions, as I have said, in the residual state the conditions are the same. So in this case also these conditions are the same. Now sample Y is undrained and the void ratio E naught remains constant, because since it is undrained, so as you know from your definitions of an undrained test that the delta V is equivalent to 0. So since delta V is equivalent to 0, so obviously the void ratio is also almost, delta E naught is also equivalent to 0, because the void ratio in case of a soil represents the volume change. So since sample X is drained, means since in this case X is drained, so obviously in this case the volume change is the only factor. So delta V is not equal to 0, so delta E naught is not equal to 0. So if you consider it to be a over consolidated soil, then in this case with the process of draining, or basically if you consider it even to be normally consolidated, with the process of draining, what will happen, the void ratio will either increase or decrease depending on whether the sample is dilating or basically compression during the shear. Now the clay is over consolidated, so obviously you know that the sample will dilate. That means the volume change in this case, if this represents the compression, because we always take compression as positive in case of soil, while you can case tension as negative in case of soil. So delta V will be in compression and then after it will increase. This is what happens in over consolidated soil, because I showed you just from the stress path diagram that this is the initial condition. Then it moved along to 0.6 MPa because it was pre-consolidated there, and then it moved back to 0.2 MPa. So as you know from the consolidation curve, this is 0.6 MPa, this is the OC line, well this is the normally consolidated line. So obviously it moved along this line and then it reverted back to 0.2 MPa. So obviously it is in the over consolidated range, and since it is a over consolidated range, you always know that an over consolidated clay will behave like this in case of stress, while basically the corresponding volume change will be equivalent to dilation. So since its corresponding volume change will be equivalent to dilation, so obviously the volume is increasing. So the volume at failure will be greater than the volume at consolidation. While for the other sample, you know that E naught is constant. So since for the sample, since for one of the samples, or since for the X sample, you see that the volume is increasing. Since for the X sample the volume is, or basically the void ratio is increasing, while for the other sample the void ratio is constant. So considering from the concept of void ratio, if you remember, since the sigma 3 is almost the same, since sigma 3 is almost the same, undrained and consolidated and drained and consolidated, for X the mode circle will again be less than the mode circle at Y. So just like the similar conditions, this is at X, and this is at Y. So Y, this is the total, and effective stress for Y. So this gap is, let us say, U, and for x it will be here. So, this is the total and effective stress, because x is drained, this is x. So, because x is drained, so the total and effective stress will be same, while y is undrained. So, obviously the total and effective stress will be different. Now, this is for the case of y, this is for the case of x. So, in case of x, the volume change is more, or basically the void ratio is more. So, obviously it is obvious that basically the shear strength in that case, or shear strength in case of x, will be less than that of y, because you already know that in corresponding to the volume change, it means it is a loose sample, or basically behaving as a loose sample, while in case of y, since the volume change was constant throughout. So, basically in this case you can say that it is almost the same behavior as it was experienced before. So, obviously the shear stress in this case is going to be more rather than that of x. Now, let us move to the last question, which says that a consolidated undrained test is conducted and the consolidation stress was sigma 3 dash. In case of x, it was remolded and recompacted to same density as y. In case of y, it was not remolded and compacted. And there is one important thing meant to mention, that the clay here is mentioned is sensitive clay. Now, as you all know that when basically in case of, if you consider a sensitive clay, then when you remold it, then it completely loses its shear strength. So, since it completely loses its shear strength, so obviously the shear strength will almost decrease to 0, because you have seen figures where basically you will see that the clay after remolding, if it is a sensitive clay, it will remolding, the shear strength, it will flow like a liquid. So, if the clay is sensitive, its shear strength decreases immediately. So, obviously in this case, without thinking much, you can say that the shear strength of x is less than y, because in this case it is a consolidated undrained test. So, I am not drawing the effective stress envelopes, but you can see easily that whether it's, since it is compared to the same density, so it does not matter that what is the effective stress envelope right now. So, x has much less strength than that of y because of its remolding nature. So, in this problem we have discussed that about how, with the help of stress paths, or how by applying basic concepts of the soil mechanics, you can actually think that what should be the shear strength, whether that when you are comparing two samples, whether the shear strength in case of a consolidated undrained test or basically in case of a consolidated drain test should be greater or less. Like I have said that in the previously, that with the increase in strain rate, like the simple inferences that we came across was that with the increase in strain rate, what will happen is that, especially in case of a consolidated drain test, with the increase in strain rate, what will happen is that it will behave more like an undrained manner. So, in this case, if the sample behaves more like an undrained manner, in this case the strength is going to decrease or increase depending on whether the clay is normally consolidated or over consolidated. Similarly, if the sample is subject to a pre-consolidation pressure greater, then obviously the sample will behave in an over consolidated manner, and obviously if it is a drain test, then its void ratio is going to increase. So, in this case the strength is going to reduce. So, depending on all these cases, you can actually find out that whether, depending on the same sample, for the same sample tested under different stress conditions, how physically you can interpret the behavior of the sample and the strength of the samples. Now, we will move to the third problem. Now, this third problem basically has a little bit concept of mechanics rather than considering all this more Coulomb failure conditions. So, in this case we will find out that how generally with the help of our triaxial test you can find out the Poisson's ratio in case of a triaxial test, and then you can link it with the consolidation test Poisson's ratio. Now, this is often considered in the field that basically you have to find out, let us say, certain parameters like E or the Young's modulus of elasticity especially, or nu, let us say, or basically you have to find out the odometric modulus or M, which is basically the inverse of 1 by mv or the coefficient of volume compressibility. Now, these cases it is not always possible, or it is you cannot always perform the same test or different types of test in the laboratory because of some certain problems. So, in this case, how or what test you should ideally perform, and how you can easily find out that what is the conditions that are to be applied and conditions to be applied, and the finding out this Young's modulus and then Poisson's ratio and odometric modulus rightly from the test. So, there are certain assumptions, however, regarding this, like suppose in case when you are finding out E, then one of the major assumption is that you have to consider the soil or the stress strain curve always within the linear elastic zone. Then similarly, in case of Poisson's ratio also you have to consider these conditions, and for odometric modulus similarly you have to consider that always the test is one dimensional, because as you know, in case of consolidation the confinement is applied from both sides. So, the test only is one dimensional, or the stress only is applied in one direction, that is why it is termed as Terzaghi's one dimensional theory of consolidation. So, depending on that you have to find out all this odometric moduluses, the Young's modulus and the Poisson's ratio. So, in this case first let us consider a linearly elastic soil, and then it is asked that the sample is subjected to isotropic stress loading. Now, right now you know all that an isotropic stress loading is the same stress loading that is applied during the process of consolidation. That means in all direction the confinement is the same, or the pressure applied is the same. So, in this case isotropic stress loading is subjected to the sample. And you are asked to find out the change in volume. Now, remember that this is a linearly elastic condition. Linearly elastic condition means everything is within this range. That means whatever the stress is applied, that is directly proportional to strain, and the ratio of stress by strain is equivalent to the Young's modulus of elasticity. So, if that is the case, then for the time being let us consider that sigma I is the isotropic stress to the soil with E. Now, you know E is the Young's modulus of elasticity, or basically this part E, and Poisson's ratio as nu. Now, from the basic mechanics definition you know that the strain can be written as minus 1 by E into sigma I minus 2 nu into sigma I. Now, 2 nu into sigma I means this is totally related to the traxal stress conditions, because you know actually it is written as epsilon x. If you consider, then it is written as sigma x by E minus nu into sigma y plus sigma z by E. Now, obviously you also know that in case of a traxial, this is sigma 1, this 2, sigma 3, sigma 3, sigma 3. So, obviously sigma y is equivalent to sigma z, and sigma x is the only factor that basically is the sigma 1. So, that is what I have written, sigma I minus 2 into nu into sigma I by E. Now, from here you can easily derive the definition as sigma I into 1 minus 2 nu by E. So, then from here you can also find out the volume change delta V by V as 3 times of epsilon I, because you know that the volume change is actually equivalent to the strain in 3 directions. Now, a detailed discussion of all this will all consider in the next lecture, which will be the last lecture for the tutorial session. So, thank you.